All right, so what are we doing? So one of the big pieces is that, again, this is sort of saying what I was just kind of connected to what I was just saying, which is, maybe we don't want to find the whole, what's the probability that we're in a component of size 3 or 4 or 5 or 6? Maybe we don't want to find all those things. But even so, it's still helpful to get to the really big stories, which is what's the fractional size of the largest component. And so this is a situation where, right, so normally with these probability generating functions, when you evaluate them at 1, you're adding up all the probabilities, right? So the x to the 1, x to the 2, they're all 1, so it's just going to be p0 plus p1 plus 2, p2. You're adding the probabilities. But there's a slightly important way we've been saying over and over, which is that these are finite components, right? What's the probability that a randomly chosen node is part of a finite component? Because if it's in the giant component, then n is infinity, right? So that's not there. So if the giant component comprises 2/3 of the system, then the probability that you're part of a finite component will be 1/3, and you'll get 1 minus 2/3 here. So feel like sneaky things happen? It's a little sneaky. So that is an interesting little delicate point of these things, and it works. So we could do this. This is to find the right. So this is the probability that our randomly chosen node pi sub. There's no pi sub 0, 0. If we've got a node, it's at least part of a component of size 1, but it's going to be components of size 1, 2, 3, 4, and we're going to add up all these probabilities. That's what this 1 is really doing, and then 1 minus that will give us the probability that we're in fact in a giant component. More Pratchett's. Okay, so we could do that. So we can get rid of x right now. We can just set it to 1, and then we'll have an easier thing to kind of mess around with potentially, right? Because we actually know this function here. We know this function here, and now we're just solving, right? So this is a fixed point equation now, right? So this is blob, function of blob equals blob, so we could solve that. And once we've got it, we can stick it into there, and we'll get this number we want. So that's plausible. You can also go back to these equations. We'll do this. You can go back to these equations here and take a derivative of the thing and set x equal to 1, and then we'll have equations we can play around with where we can try to find the average size of a finite component. Okay. Right. It's often numerical, but we'll have a simple equation. Again, the core equations, right? Just I want, it's sort of, if this is a confusing thing, but as you come back to this and look at it, these are the two core equations that describe everything for that we're interested in here for our random networks, and they connect to those two pictures that I've been showing you, right? That's the encoding of those two pictures into generating functionology. Yeah. So it may seem slippery at the moment, but that just get those. You can just say that to yourself that those things are the same thing. All right.